Hello guys, welcome back to another tutorial. In this tutorial, we are going to talk about FPGA. So if you have not watched my first video, so I suggest you to please click the link above before watching this tutorial. So let's get started. So what are the tutorial objectives of this tutorial? Well, we are going to start from the introduction of FPGA. We are going to start from the definition of FPGA. Then we are going to dive into some of the very basic concepts of FPGA. In second objective, we are going to cover Altera FPGA, which is the development board that we are going to use throughout the course. And in the third objective, we are going to talk about some very basic concepts of Verilog, which is the programming language that is going to be used to program the FPGA. And finally, we are going to use the concepts that we have learned in the third objective to program the FPGA. So, when we talk about FPGA, the first thing that comes in our mind is why FPGA? So if you are familiar with the combination logic circuits or digital circuits, you know that for implementing a very basic combination circuit or digital circuit, you have to take several different ICs for each logic gate. Like you have to take an AND IC, OR IC, NOR IC to implement a very basic 2-level or 3-level combination logic circuit. So hardwiring several different ICs is a very complex process, and another disadvantage is it requires an excessive amount of area on a PCB that will be consumed by requiring several different ICs for each logic function. So to overcome this problem, first PLD was developed in 1956 as a PROM. Then there comes an EPROMs and finally PLAs to PLDs. So what is a PLA? Well, a PLA, a programmable logic array, implements a 2-level combination logic circuit in SOP form, whereas SOP stands for sum of product, whereas a PLD, which is called a programmable logic device, contains thousands of basic logic gates plus advanced sequential logic functions inside a single package. So this is the block diagram of a PLA and this is the block diagram of a PLD. The PLA, as you can see it here, consists of an AND array which forms the product term, which is also called mean terms, and it also consists of an OR array which takes these mean terms, product terms to form the outputs. So in this way, the PLA can produce any form of Boolean equation or a combination logic circuit. You just have to program the AND array and an OR array, so you don't have to wire several different ICs like you do in the past. So this is the block diagram of a PLD. It consists of an AND plane, it consists of OR plane and some buffers and inverters. So well, there are mainly 4 types of PLD. The first one is SPLD, which is called Simple Programmable Logic Device. The second one is CPLD, which is Complex Programmable Logic Device. The third one, which is our main topic, which is FPGA, Field Programmable Gate Array. And the final one is ASICs, which is also called Application Specific Integrated ICs. So, what is FPGA? Well, an FPGA is a semiconductor device that is based around a matrix of configurable logic blocks connected via programmable interconnects. So, FPGA consists of 3 major elements. It consists of configurable logic blocks, which is called CLBs, programmable interconnects, and IO blocks, which is called IOBs. So this is the FPGA architecture. These are the programmable interconnects. These are the IO blocks, which is IOBs. This is the CLB. So before we understand the architecture of FPGA, if we just start from the SPLD, so SPLD is nothing but simply a PLA, which is also nothing but simply a plane of an AND array and an OR array. So SPLD is a PLA, and if we talk about CPLD, so a CPLD is also nothing but simply several PLAs combined together, connected together to form a macro cell, which is also called as lab, which stands for logic array blocks. So a CPLD is also nothing but several PLAs are combined together, connected together to form a macro cell or a lab. So FPGA is very similar to a CPLD, but instead of connecting several PLAs to form a macro cell, it uses a lookup table method to resolve a particular logic requirement. So CLB consists of logic modules like PLAs, but this logic modules performs the function of several logic gates, but it is less complex as compared to lab or macro cell in a CPLD. So CLB is used to implement a combinational logic gate and a register logic as well. So in a CPLD, there is a LUT which is associated with a SRAM based memory element to develop SOP expression. So what is a LUT basically? A LUT is used to implement a truth table, and if you know a truth table, you have a combination of inputs. So this combination of inputs, also called as addresses, these addresses are stored in the SRAM based configuration memory. So this helps us to change only the combination of inputs in the SRAM to implement any logic gate or Boolean equation. So in this way, the LUT are very important parameters, very important block of a CLB. So in this way, FPGA are very denser and faster than a CPLD. So these are the CLB, and if we talk about programmable interconnects that are used to connect various CLBs together, like if you have a very complex digital circuit, that then obviously it will require several CLBs to connect it together. That's why programmable interconnects are used, and these programmable interconnects are also two types, uh, mainly local interconnects and global interconnects, whereas local interconnects are used to connect uh, two CLBs that are close together, whereas global interconnects are used for long distance communications. So these are the programmable interconnects, and IOBs. Each IOB is also programmable with logic buffers and transistor devices for compatibility with TTL and CMOS signal levels. So if you know TTL signal levels, in a TTL devices, you have 0 to 0.8 something considered as low signal level, whereas 2 to 5 volt is considered as high, whereas in a CMOS signal level, you have 0 to 1.5 considered as low, whereas 3.5 to 5 volt is considered as high. So this is the TTL and CMOS signal levels. So as IOB with logic buffers in it, uh, and transistor devices are used for compatibility with TTL and CMOS signal levels. So IOBs has numerous number of inputs and output pins, up to thousands, which can be used as input, output, and also bidirectional. So this is why you can declare any pin of FPGA as input, output, or bidirectional. So this is the architecture of FPGA. So this is the development board that we are going to use throughout the course. So as you can see here, this is the main IC, main FPGA, which is Cyclone to Altera, and as you can see it here, this Cyclone to Altera FPGA consists of 35K logic elements, which is also called as CLBs. So this FPGA consists of 35K CLBs. So this development board also has mic input, line input and output for speakers. This is the video input, VGA input, also RS-232 LAN, and it is powered by a 9-volt battery and a 9-volt charger. It has also an LCD, 16 by 2 LCD. 7 segments, some push buttons here, and some switches, and it is all there are also an SD card socket, and this PS2 is used for connecting mouse. So there are many things here for on this development board here. So this is the block diagram of the development board. As I show you here, this is the block diagram, and in this block diagram you can see here for audio devices, this IC is used, which is called WM8731, and we are going to cover this as well. We are going to program this as well in the future tutorials. This is ADV7180 TV decoder for connecting TV and or other thing as well. So this is it. We are not going to talk in detail. These are the hardware specs of the development boards. You can rate them here. So we are not going to cover them. So now we are going to start from the from the third tutorial objective, which is the Verilog. So first of all, we are going to talk about HDL, which is called Hardware Description Language. So the FPGA configuration is generally specified using an HDL, similar to that used for ASIC. So if you are going to program FPGA, you need to learn HDL, Hardware Description Language, to program the FPGA. And there are two popular types of hardware description language. One is called Verilog, and another one is called VHDL. So these are the main points of Verilog and VHDL. Verilog is easy to learn. It is similar to C language and not highly tapped. That's why we are going to use Verilog in all of our tutorials. We are not going to use VHDL because it is very comparatively difficult to learn, and syntax is also not similar to C language and highly typed language. That's why we are not going to use this language in our tutorials. So now we are going to talk we're going to start the third tutorial objective, which is the very basic concepts of Verilog. So in a Verilog programming language, we have a module. Every Verilog program will have a module, which is declared by a module keyword module, then followed by a name of the program, which I call it as my design, then followed by a parenthesis and some inputs and outputs, which is called ports. So input and output signal of a module are called ports, and they can be as inputs, outputs, and or bidirectional, which is in out. So every Verilog program will be declared as module, followed by the keyword name, the name of the program, followed by the input and output signal in a parenthesis, and for this module will be closed with a keyword and module. So everything between module and end module will describe your logic. So this is the main syntax of Verilog uh, in every program that you're going to type, that you're going to program using Verilog. So you have to declare the module and module, some ports, the name of the program, and etc. So there are two Verilog modeling styles. Number one is structured modeling, and the second one is behavioral modeling. And in structured modeling, we are going to use predefined or user-defined primitive gates. And what are these primitive gates? We are going to talk here. And in a structural design, it is very similar to creating a schematic. Like if you have an AND gate, OR gate, NOR gate, and you are going to connect them together, then basically you are going to form a schematic. And in a structural design, it is very similar to form a schematic when you are going to connect these logic gates together. So what are Verilog primitives? Well, Verilog includes a set of 26 predefined functional models of common combination logic gates, which are called primitives. So if you have an OR gate, NAND gate, AND gate, and etc., then you just need to use their keywords, and you don't have to write combination logic circuits and Boolean equation. You just need to use their keywords and you're ready to go. You don't need to write their combination logic circuits and truth tables as well. So You just need to use their keywords. That's why Verilog primitives are very useful in structural modeling designs. And in structural modeling, each primitive has input output ports. Obviously, if you have an AND gate, then possibly you may have two, three, or four number of inputs and a single output. So their functionality is built into the language by means of internal truth tables. So, behind the scenes, these internal truth tables are used to form a Verilog primitive. Like if you take an example of an AND gate, then this AND gate truth table is internally used in the Verilog programming language to form this Verilog primitive of an AND gate. So this is how Verilog primitives are used, because behind the scenes these internal truth tables are used in a Verilog programming language in a structural design. So this is the methodology of structural designs. The output port of a primitive must be first in the list of, followed by input ports. So if you have an AND gate, this is the primitive, and you are using keyword AND. So this is the Verilog primitive. So in the Verilog primitive, you are going to declare the output port first, followed by the input port. So if A and B is the output, if A and B is the input, then X, which is the output, must be declared first in this primitive. Like if you have an OR gate, the output Y must be declared first, then the inputs, which is C and D. So the Y can never be declared after C or after D. So you must declare the output first when you're going to use Verilog primitives. Like in a NOT gate, Z is the output, so it is declared first. So this is the first line that is describing this concept. And a primitive is instantiated within a module by a statement declaring its keyword. So if you are going to include a Verilog primitive, or you're going to instantiate a Verilog primitive, then you just need to include its keyword. Like if you are going to use an AND gate, you just include the keyword AND. If you are going to instantiate or include a keyword or include a primitive OR, then you just instantiate or include a keyword OR, and same is true for NOT gate as well. So this is the main methodology of structural modeling design. And the next one is structural connectivity. So the variable type wire, which is the keyword wire, is a family of net which is used for establishing connectivity. So wires are used in a structural modeling designs for establishing connectivity, and it is a family of nets, which is also a data type used in behavioral modeling. So we will talk about them as later. So wires in Verilog connect primitives to other primitives and or modules. So if you take example here, so this AND gate is connected to this NOT gate, and this OR gate is connected to this AND gate. So how they are connected? They are connected using a wire variable, using a variable of type wire. This AND2 is a variable of type wire. So these wires are used to connect this AND gate to this OR gate, and this wire is also used to connect this OR gate to this AND gate, and etc. So in this example, first of all, we are going to declare the keyword module, then followed by the name of the program. We are going to call it as my design. Then since there are three number of inputs, we call them ABC, so we declare them here. You are free to name it in any order you want. If you are declaring y n1 n2 n3 and then ABC, then you are ready, then you are free to do that as well. So that will do nothing wrong with the program. So ABC is the inputs, are the inputs N1, N2, N3, since they are also the part of the circuit, and they are outputs of these gates as well. So that's why we are going to use them in the list of ports. So we are going to include them in the ports. So now we are going to define them, which of these are inputs and which of these are outputs. So inputs are ABC, and outputs are N1, N2, N3, and Y. So since N2, N1, N3 are also of type wire, so we declare them output wire. So this is how the program works. Now we are going to instantiate or include the Verilog primitives like NOT gate. Since the output of NOT is N1, we are going to include N1 first, followed by the input, which is B. When B is here, then we are going to instantiate the Verilog primitive and since and output is N2, we are going to declare it first, then followed by the input A and N1. So this is A and N1. Second, we have AND gate, another AND gate. Its output is N3. We are going to declare it first, followed by the input B and C. So we declare them afterwards. And finally, we have OR gate, which whose output is Y. So we declare it first, followed by the input N2 and N3. So this is how the structural modeling design works. So now we are going to talk about behavioral modeling. This is the second Verilog modeling style that is most often used by expert programmers. So if you take a closer look to structural model, so structural model is only good if a design involves few gates. Like if you have less number of inputs or less number of gates, then you're free to use structural model. But as the number of gates or as the number of inputs increases, the structural model is becomes very difficult to handle, because as the number of inputs or as the number of gates increases, you have to declare as many variables of type wires for each logic gate or for each number of outputs for each number of gate. So number of variables increases, and when this number of variable increases, it becomes difficult to connect them together properly to create a proper schematic. So that's why structure model becomes very difficult in creating a complex digital circuits. So in these scenarios, we have a second Verilog modeling style, which is called behavioral modeling. And in behavioral modeling is the predominant descriptive style that can be used in such cases and is adopted by expert programmers, enabling the design of massive chips like ASICs. So that's why we are going to use behavioral modeling in many of the tutorials in the future, because we are going to design very complex circuits as well. So as far as the beginner level is concerned, structural modeling is good, but as far as the complex digital circuit is required, the behavioral modeling is very acceptable. So what are the data types of behavioral modeling? So we have two data types. Number one is net, and the second one is register. So a net variable act like wires in a physical circuit and establish connectivity like wire variable, but net and wire are very similar but not same. And there is a register variable also. Register variables act like variables in ordinary procedural language. They store info only on the clock pulse. That means that if you take an example of a C or a C++ language, you know that you have variables of type char or float or integer, which stores some info. But register variable in Verilog will store information but only on the clock pulse. So register variables, that's why they are very similar to variables in ordinary procedural language. Wire and registers has a default size of 1 bit, and the keyword assign declares a continuous assignment. So when you are going to create a combinational logic circuit, you must have to declare the left hand side variable with a assign keyword. So this is how you are going to tell uh, the compiler to declare the right hand side on its left hand side as a combination logic circuit. So this is how it is done in the behavioral modeling approach. And finally, we have now completed our third tutorial objective, which is learning the Verilog basics. So in the next video, we will program the FPGA using the material we have learned in the third tutorial objective. If you have not subscribed my channel, so I suggest you to please hit the subscribe button down below so you never miss the next video of this FPGA course. Have a good day.